Hello, in this video we're going to talk about two new proof techniques to try to prove something via contradiction or contrapositive. So far in this course we've been proving statements that we can prove with a direct proof, but sometimes that isn't possible or sometimes it's really awkward. So today we're going to learn two methods that you can use if a direct proof doesn't seem like a good idea. We're going to learn how to formulate the contrapositive of an implication. And we're also going to learn how to prove an implication using contradiction. We're going to prove the same statement via contrapositive and contradiction, and then we'll compare the two proofs to see how they're similar and how they differ. And that will help you hopefully strategize about the kind of which proof technique you want to use. Okay, so recall, the situations in which the statement, if P, then Q, or equivalently, P implies Q, and it's contrapositive, if not Q, then not P, are true, are summarized in the truth table here. So the two statements are logically equivalent. How can we see that in the truth table? So in the left-hand two columns, you can see P and Q and all possible combinations of true and false values for them. And we remember that an implication P implies Q, or if P then Q, is true except for the one case when the premise is true and the conclusion is false. That's the one case that's not allowed. Now, in the next two columns, you see not P and not Q, and all possible true and false values for those. You can see in a row, if P is if P is true, then not P is false, and vice versa, same for Q, okay? And what you can see then, if you just focused on these three columns in the truth table and said, okay, so in the first row, so I have not Q is false. And remember, if the premise is false, the statement is automatically true, the implication, right? So that's why the first row is true. And in the second row, you have not Q is true, but not P is false. And that's the only time an implication is false, when the premise is true and the conclusion is false. And that's why that row is false, okay? And so you go through the rest of the truth table, and if I just paid attention to the part in the red braces, I would get true, false, true, true. But then I look at this part, which I've got in blue, and I see, wait a minute, those two columns have exactly the same truth values in them. And that's how I interpret this truth table, as telling me that P implies Q and it's contrapositive, not Q implies not P, are logically equivalent, okay? So I can do a direct proof of if P then Q, or I could do a direct proof of not Q implies not P, and I'd be proving the same thing. So why would I want to do this weird thing of prove the contrapositive? So here's a statement where it seems like it just might be easier. Let's quickly see what would happen if we tried a direct proof. So try direct. So what would we do? The assumption is that n squared plus 2n plus 3 is even. So we'd say, well, that would mean that n squared plus 2n plus 3 equals 2k for some integer k. And then we look at it, and you know what? Like, I don't know what algebra necessarily to do next. There's the square there. It's a little tricky. So that's when I say, let's do something simpler. And the tip-off here for doing something simpler, I would say, is that the quantity or the expression in the assumption is more complicated than the expression in the conclusion. okay? So it's a little bit easier to flow from a less complicated assumption, plug that into the more complicated formula, and get a conclusion. So let's turn this around using the contrapositive and see if that'll work for us. Okay, so for the first proof, I'm going to say proof. And in a proof like this, it's good to signpost for your reader what your intentions are. Okay, so I'll say, will prove the contrapositive. And remember, we want to try to take the cognitive load away from our reader, right? And interpret things for them. So I'm going to say, i.e., if, and so I've got to do the negation, excuse me, of the conclusion. So if n is even, then n squared plus 2n plus 3 is odd. So I've negated the conclusion and then negated the assumption, the original assumption. Okay, so now I can say since n is even, there exists an integer k such that n equals 2k. Therefore, when we look at n squared plus 2n plus 3, that's equal to the quantity 2k squared plus 2 times 2k plus 3, which is 4k squared plus 4k plus 3. And now I have to remember, I've done some algebra, I've simplified things. What conclusion am I trying to draw? I'm trying to draw the conclusion that n squared plus 2n plus 3 is odd. So I want to write it as 2 times an integer plus 1. And what I can see is that I can rewrite this as 4k squared plus 4k plus 2 plus 1. And this part is even. It's equal to 2 times 2k squared plus 2k plus 1. And so now I'm just going to move this. Let's see if I can move this down a little bit. Okay, I'm going to put a period here. Therefore, that's true. So, or maybe I'll say since. Since 2k squared plus 2k plus 1 is an integer, n squared plus 2n plus 3 is indeed odd by the definition of an odd number. Therefore, though, let's conclude the original statement. So we've proven the contrapositive, and we can say, therefore, since the contrapositive holds, so does the original, which is that n squared plus 2n plus 3 even implies n odd. Okay. So one nice thing about proving the contrapositive then is that once I turn the statement around and formulate the contrapositive, I'm just doing a regular old direct proof in the middle. And then my final interpretation is that the direct proof of this changed around statement is logically equivalent to what I started with, right? Let's see how the proving the contradiction is different. So let's go back to our truth table over here. And I want you to look and see, so in a proof by contradiction, what we're going to do is assume the thing we're trying to prove is false, and then reach by taking that taking that position. We're going to work logically and correctly and arrive at something we know is absurd, and that will lead us to conclude that our original assumption that our statement was false is not true. It has to be true, okay? So let's look at this truth table and think, well, when is this statement false? And we see there's only one line in the truth table where the statement is false. It is right here, the second line, where the situation where P implies Q is false is exactly where P is true and Q is false. And that and is really important. And this is often a little confusing when people are first learning how to prove an implication by contradiction. People sometimes want to assume that Q, like P is true and implies Q is false, or something the other way around, I don't know. But you want to assume that P is true and Q is false. So you're assuming those first two something with the first two columns of the truth table. Okay, so let's try to do this. So proof. Again, we're going to signpost for the reader that we're going to do a proof by contradiction. So we'll proceed by contradiction. So we'll assume that n squared plus 2n plus 3 is even, and the conclusion is false. N is even. Okay, now let's see what happens next. Well, we'll say, let's see, since n is even, there exists an integer k such that n equals 2k. All right, and now I have my two assumptions that n squared plus 2n plus 3 is even and n equals 2k, and I have to find a contradiction someplace. Well, let's see what will happen. We can say since, or say therefore. Let's say therefore. Let's see if it rings any bells. Therefore, what we see is that n squared plus 2n plus 3, which is the quantity of interest, if n is even, we can plug 2k in for n. We get 2k quantity squared, 2 times 2k plus 3. I'm running out of room, so I'm going to write horizontally a little more than I would otherwise. And this is 4k squared plus 4k plus 3. What's happening here? Interesting. This is looking a lot like the computation we had above. And I'm going to say, well, oops, what did I do there? Well, I'm not going to redo all of the algebra, but maybe what you can see is that this is going to be, because it's exactly the same quantity as before, 2 times 2k squared plus 2k plus 1 plus 1. And then I'll say since 2k squared plus 2k plus 1 is an integer, since it's in Z, what we can see is that n squared plus 2n plus 3 is an odd number, because I've written it as twice an integer plus 1. But wait a minute. In this proof, what was my assumption? My assumption was that n squared plus 2n plus 3 is even. Okay, this is the contradiction. Oops, let me get my black pen back. So this contradicts our assumption. And so since we have a contradiction, it must be then that that's false. Therefore, we conclude, oops, that's not how you spell conclude. We conclude that n squared plus 2n plus 3 even must imply that n is odd, because certainly if we assume n squared plus 2n plus 3 is even and that n is even, we get this absurdity, right? We conclude that n squared plus 2n plus 3 is odd, but we've assumed it's even, and so that's a contradiction. So what happened there? So again, I'm keeping the proofs relatively simple so we can focus on the logical structure. And what we noticed is that it's really just the first sentences that are different, and then the last sentences that are different. The algebraic substance of the proofs are exactly the same, right? Where I said, since n is even, there exists a k such that n is equal to 2k, therefore, blah, 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 blah. That happened in both proofs. What I often have students do in class, so I had students break up into two groups, or two pairs of groups, and I say, one half of the room, you prove this statement by contradiction. The other half, do the contrapositive. What always happens when I do that is the side of the room that gets the contrapositive proof finishes way before the side that does the contradiction proof, even though the algebra and the proofs are exactly the same. And I think what's going on is that proofs by contradiction are just there's like an extra step of cognitive load in there, where you have to sort of process, like, you're doing this thing, and then at the end, there's this extra interpretive step. So I guess I would say, if you have to do a proof by contrapositive or a proof by contradiction for an implication, what's going to happen in the proof, like the substance of it, is going to be the same. And you might as well do the contrapositive one, because I think those are logically more clear. I think those are just logically more clear. We'll see later on in some of the number theory proofs that there are some proofs, statements that aren't implications, that you still need to prove, and you can't use a direct proof. And sometimes there you have to use a contradiction. But a contradiction is always, I don't know, I think it's kind of a proof technique of last resort, because it doesn't really tell you, in some sense, it doesn't tell you why something is true. It just tells you why it can't be true. And it's just inherently a little less satisfying. Anyway, we'll have lots of practice in class.